So I've started the recording. Good evening, everyone. I'm Prableen Kukreja. I'm working as a PhD scholar, giving my intro. I'm working as a PhD scholar in IT Tirupati. So whosoever has not seen the previous lectures, you can see the previous lectures in the YouTube channel. I have written in the chat box the channel name, as well as you can also email me in whichever point you are getting difficulty. Like I get the emails from the other people as well. I have got some I don't think so. She's present today. She usually frequently Chavi. She is frequently mailing me this. Like you can also mail me like her and others also. Like they send me the screenshot also where in which point you are having the difficulty. I'll explain you that also. So this is my Gmail ID as well as the YouTube channel. So let's start the session. So till now, okay. So till now, whatever we have covered is like we have started with the machine learning. Though I'll not go again with that. Just I'll tell you whatever the things we have covered. We started with the introduction of machine learning, the supervised learning, unsupervised learning introduction. We have gone in much depth about the loss function, the statistical decision theory. Ma'am, on the channel, do you upload these? Yes, yes, I do upload these doubt sessions, Samriddhi. So, we have gone in detail about the statistical decision theory, the loss function. Like in much detail, we have gone like how step by step the things are going. Then yes, then we have gone through a bias and variance trade-off. Bias, what is bias, what is variance? I have told you in much detail, like by giving a very simple example also of overfitting and all. Then we have gone through the linear regression part and how to find the parameters, the gradients and everything. Multivariate regression we have done. And then we went to the shrinkage methods. Can someone tell me what are the shrinkage methods? Whosoever has attended the last lecture. Yes, let's give a try. It shouldn't be like I am speaking and you guys are listening. It should be two-way. Stop me whenever you are not getting the things. I'll repeat it 100 times, I'm saying. Stop me, mail me, wherever you are having the doubt. So can someone tell me about the shrinkage methods? Yes, anyone? Yes, we have covered last time only.
One of them is subset selection. You can shrink the subsets.
So we did the subset selection, in which in subset selection we did forward stepwise selection, forward stage-wise selection, backward stepwise, and all. And these are the topics which I have covered. And then we came up with lasso regression as well as ridge regression. Last time in the last class, we were discussing about this. So can someone tell me like what we have discussed in the last class? What is this lasso regression and ridge regression? These are actually the shrinkage method that is the subset selection methods, that stepwise and stage-wise. I also got confused. Yes, can someone tell me what is lasso and ridge regression? What is regression? Why we are doing it? Why we are shrinking it? There are so many questions in our mind. What is this? What I have written? Can someone tell?
Ma'am, lasso regression is to making the gradient to zero, whereas this regression is not making to zero.
Absolutely.
Yeah.
So can I say I am reducing the coefficients in both of the cases? I'll go very easy words. I'm reducing the coefficients in both cases. Like what I'm trying to do is, like, suppose I have 0.4 plus 1x1 plus 20x2 plus 30x3. So by this regularization, these are basically regularization methods. What we are trying to do is, we are trying to reduce the coefficients. Trying to reduce the coefficients means whatever the coefficients are here. Like here, instead of 1, I'm trying to reduce it to suppose 0.7, it is reduced to 2, it is reduced to 5. So these coefficients are basically getting reduced. That is the main motive of this this normalization or lasso regression and ridge regression. As you have mentioned very well, that in lasso regression, we are reducing to 0. Last time also I told you how. Can someone tell me again? And why we are reducing? First of all, before jumping to, okay, we are reducing it. We have done covered in last lecture, just a recap. Why we are reducing it? Can someone tell me?
Ma'am, to reduce the model complexity, we want the coefficients to be less.
Yes, yes, yes. To reduce the model complexity. In one way, we can also think that they're computationally.
Computational also we can complexity as well as, and also unwanted features we can eliminate because which are not giving the like value to this that prediction. So we can reduce those actually. Unwanted, otherwise unwanted noise will be counted.
A very good point. That unwanted features which we don't want, that can also be reduced here. Like obviously some features, we don't want so many features. If I talk about lasso regression, feature selection, that I'll come to this lasso regression. In lasso regression, that is a very good point. So how we are reducing now? The other question.
Through penalty.
Through penalty, we are adding the penalty in the loss function. Last time I gave you just I told you, tell me like how by adding penalty it's reduced. You were asking me, I said you, okay, let's take an assign homework problem, like just a small, how by adding penalty it's getting reduced. You got that point or no? We are adding the penalty, we are reducing the coefficients. What is penalty here? Like suppose alpha, this is either the squared norm or either the norm, simple norm. This is in the case of rich, and this is in the case of, this penalty is in the case of less. What does this stand for? This stand for W1 square plus W2 square, so on. And by adding this penalty, and when this penalty, this alpha term is high, the coefficients are reduced more. How? Can someone tell me? How by penalizing? What is the penalty doing? Penalty is reducing the coefficients. How it is reducing the coefficients? You only were asking me about this, like, ma'am, how it's reduced. So I gave you, like, okay, you tell me, like, how it's reduced. In last lecture, we did this. Okay, I'll come to this only. I'll not write again. So this was the loss function. This is W, can someone explain me what I have written? Again, I'll come to you. Wi minus beta naught minus xi beta j. What is this?
This
In
is the
this,
normal
we are
regression
trying to.
line.
Loss function, can I say? Regression loss function.
Yes, ma'am.
Yes.
So what we are trying to minimize it, and then we are adding this penalty term on it. And then what we did, we tried to find out, like by differentiating and like we opened this bracket, we wrote it in the form of I'll say in the matrix form, and then we have done this and we tried to find out the beta range. That is what we have done. What is the value of beta? In linear regression, what is the value of beta? Can someone tell me? We have find out. This was the value of the beta. We have differentiated and we have tried to find out this was in the normal the value of beta. But in the regression, we find out this is the value of the beta. Am I correct?
Yes, ma'am.
Now, can you tell like by changing the values of lambda, the beta will change? Okay, I'll come here. Now I told you that beta is equal to beta in ridge regression is equal to x transpose x plus lambda I inverse. We have find out and x transpose y. So
This is ridge regression beta, right?
yes, I should write that ridge. Now suppose let's take it as x transpose x value is suppose 10 0. I'll not write whole because it will take a lot of time. Just simple I'll just solve it like just by taking I'll say normal toy example. Suppose these are the values I'm not solving. Suppose I got this. I have to solve this to calculate the beta. That's what my main motive was. Like this is simple beta without lambda. And when I'll do this lambda, x transpose x plus lambda I inverse, then I'll get the beta as lambda value is suppose here 1 or 10. Then my beta values will actually be reduced. So when I'm adding this penalty term, this lambda, this one, actually when I calculate the beta values, they actually get reduced. The coefficients get reduced. Are you getting my point? That's what the benefit of this penalty term is. We started the lecture why we are adding the penalty terms to reduce the coefficient size. Why we are doing so? So that it should be computationally less expensive. Features should be like feature selection should be there. Like lesser features should we want the more important features. We don't want the so many features in a problem. So that model complexity, on the other hand, should be reduced. How can we do it? When we are trying to solve the beta, we'll see that whenever we'll add this lambda term and whenever this lambda term will increase, the beta value will actually decrease. Got my point?
So essentially, we're just recalculating beta.
We are recalculating beta just by taking, in the last class only, we have done by just by taking this penalty term in account. Whenever we'll do this penalty term in account, we'll see that actually the beta values do decrease basically. Now coming to lasso regression. Last time, many of you were having the confusion when I was talking about this example. So have you are the things cleared? Yes, last time or again there is a confusion? What I was trying to say again, I said you that we'll basically start from this only. So I was trying to say that as one of you I think mentioned in today's class only that in lasso we are basically lasso regression. We are trying to make the coefficients 0 here. Or in other words, it's used for feature selection. So what I told, okay, it's like loss plus penalty, the same way in ridge regression. But here we are using the L1 norm. Rather than beta j square, we are using only beta j. So what's the difference? Why here we are having the coefficient 0 and why not in ridge regression we are having the coefficient 0? More probability of feature selection, why it's here? Someone told me in today's class only that, okay, we are, I think Shyamal Kumarji, you only told me that like 0, the coefficients are transformed to 0 in the lasso regression. Yes, someone, why here? In last class only I have explained. Come on. Then we'll today move to the next class. I gave you an example in the last class as well. Again, I'll take the same example. What is the difference between them? 1000 minus 999 is
1.
1. Yes, yes. And 1 minus 0 is 1. So, and what about 1000 square minus 999? It's obviously much larger. And 1 square minus 0 square, it's much, much smaller. This is we are doing in lasso, and this is we are doing in ridge. Till now, any doubt? In ridge, we are basically seeing the magnitudes. In lasso, we are the penalties basically in the square terms. Fine. Now, whichever penalty is more, ridge will choose that. Whichever penalty is more, lasso will choose that. So that more coefficient should be reduced, so that beta value should be reduced more. So lasso sees that both of them are having the same coefficient, so it can choose 1 to 0 as well. It will treat each coefficient as same only. It will treat all coefficient reduction equally. But here, it will choose this one because here it will see the penalty is much larger than this case. So that's why more probability in lasso is to go to 0. Here, if it has chance also, it will never choose this because it will always have lesser penalty than this one. Why I'm not getting any response from you guys? Are you getting, or it's going above your head? Come on. Yes.
This is the last session,
Ma'am,
but
wouldn't square
the
be
other
1 minute, one by one. Yes. Yes.
ma'am, this when you told in the last session, we got this, but the thing that you told that mean,
Yes, yes.
ma'am, I don't remember that one thing that you told that was the thing about NPTEL.
I'm
After
not.
this, you told that.
What I told, I'm not getting this. I asked you, and okay, the other question was how the shrinkage is actually happening. How by adding the penalty term, beta is basically reducing. So I told, so that's the reason when we are calculating the beta term, there we have this plus lambda I, and when we'll solve it, we'll see that the beta term will actually get reduced by increasing the lambda size. You asking about this, Chavi?
Yes, no, ma'am, not this. In the lesser regression only, you were trying to differentiate how it will tend to 0, and how the coefficients will be smaller or be reduced to 0. So that we got, but then you were explaining.
Now you
I
got
don't
this.
remember that one thing.
Okay,
Yes,
maybe
ma'am.
you can see, and you can. I also don't remember. Okay, you can ask me afterwards. I think this. What about others? Yes, someone else was also speaking. Yes, Gaurav.
So I understand that if you reduce it by 1, then lasso can go to 0, but ridge will not go to 0 because it's 1 square minus 0 square. But
It's yes, yes.
then wouldn't ridge be computationally heavy and lasso be little better?
So it do depends on the lasso. If sometimes they say if we have to do the feature selection, obviously here the features are basically 0. Suppose I have given you the example also. Here, this was the diagrammatically I have shown you. Ridge here, it is having all the features. Maybe they are reduced in size. Here, these features are actually 0 only. These features are basically actually 0. There is only feature selection. Out of 10 features, I'm selecting 5, suppose. That is in lasso regression. That works like that also. In ridge regression, all 10 features will be there, though their coefficients will reduce. The size of coefficients will reduce. So in that sense, yes, lasso is better than the ridge. but there may be, I'm not able to recall the applications. There may be some applications where bridge will also work better. Maybe I'll come in the next class with that. There can be some applications where we need all the features, but the coefficient size should be decreased, where we don't need actually feature selection. So this is just to say that lasso is more likely to draw coefficients to zero actually. And that's why we also call it as sparse regression. And calling it as sparse regression means because we are basically converting these features to zero. So we have the less memory. Like we have. Are you aware of the sparse metrics? First of all, I'm also working in research sparsification only. Are you working know about sparse metrics?
No.
Okay. So what about others? What is sparse here?
Sparse matrix is that is a square type of matrix that two-third element of this matrix will be null.
So many of the elements are basically null here, basically zero here. So that's what we are here also doing. We are actually doing the like features to zero. What does sparse matrix do help like to us? Like what is the help which is giving the sparse matrix by converting the elements to zero? How it is helping us? If I have to suppose I have I have some devices, I have to send the matrix here by doing the sparsification, by converting it to sparse matrix to the server, suppose having in the real time, suppose these are the clients or devices. How this is helping us, the sparse matrix rather than the sparse. Suppose this is 3x4. Now this is also 3x4 matrix. I'll take 30x40, suppose 30x40. Now this is also 30x40. How this is helping us by converting some elements. Now here some elements are basically zeros. Here all elements are not, none of element is zero. Here some of the elements are zeros. So how this is helping us, anyone? Yes, come on.
Does it give the like storage and efficient storage and computation kind of things?
How like I'm getting your point. You are directing towards the right thing. Like it's storage, less memory. Yes, this is only the advantage. But how it's helping is in less memory and storage. But actually, if I talk about like transfer, it's transferring the same amount of metrics, 30x40 only. Can I say, like, suppose here in the matrix, 5 elements are there which are not zero. So I can only, rather than sending the whole matrix, what I'm sending is I'm sending the 5 elements as well as their index number. And by sending them, I'm reducing this 30x40 whole matrix storage space and everything. Though I'll not go in detail, this is out of the scope. I'm sorry for that. Again, everyone will say like it's getting tougher to understand. Just I'm trying to give you an intuition.
And it's like it's more like instead of sending the entire matrix, you are just kind of compression kind of thing. Like you're just sending the like where the position is. So you're sending only that data. Rest of the things you're not sending, right?
Yes, yes.
That's why.
That's why
Yeah.
sparse matrix, sparsification help us. That's where it helps us.
Sure.
Just one. Are you trying to factorize it matrix into its lower and upper so that it becomes,
Yes. That's what I was
that's
trying.
what you're trying to say. Okay.
So, any doubt? Don't and don't think about the sparse matrix a lot. This is just I was giving an intuition why how the sparsification do help us, sparse regression things or when we convert these things to zero, how this help us like by storage and all. This was just a real time example I was trying to give you. So now let's proceed to today's topics.
Ma'am, I have one like could be a silly question, but can you please tell me that very high level, like these are these regression of feature selections is like kind of pre-processing, right? So what is done before, like what is done after, or what is done before, like one after another, like regression is done first or feature selection, like how it is done in usually.
So usually obviously
It's
this
a
is like
pre-processing.
this
And
is processing thing only. Like we are normalization means like we are basically doing this parts regression. We are doing something like this lasso regression. We are suppose we have
okay,
so many features like
okay,
a large model. We have to first reduce its complexity, then we have to send it. Suppose this can be helpful in like this can be helpful like you can think of compression techniques. Like don't go straight away to compression. Like you can think about this. Like obviously the model, when we are reducing the weights and all computationally also, and if we think about network, trying to relate about network, we have to send it. So that then also we have to reduce our model size. So for those things, when we are selecting the features, we are reducing the coefficients. This pre-processing is helping us before actual model we are applying. Do you got my point?
sure, I got it. Yeah.
Excuse me, ma'am.
Yes, yes.
Ma'am, I recalled my doubt. Can I ask it?
Yes, yes.
So ma'am, in last class, we were discussing that in lesser regression, we have lower penalty. As compared to ridge regression, lesser regression's penalty is less. So I was asking that how is it that when penalty is less, it is still giving us a lower uh, coefficient?
Penalty is less and it's still giving us no actually okay.
ఏంటి భవిష్యత్తు అదే నువ్వు పెట్టిన కాడికి నన్ను ఉడికించే భవిష్యత్తు
Please mute yourself if you don't have any doubt. Yes, can someone answer? Like if what she's asking is, if we have, I'm not saying that it's giving me low. Like what I'm saying is, I have a coefficient from 1000 to 999. Okay, and I have a coefficient from 1 to 0. They both are same. Now, what I'm saying, Lasso will choose this one rather than this one. They both are giving me same penalty in Lasso. Am I correct by saying this?
Yes, ma'am.
They both are giving me same penalty. So Lasso will choose any one of them. For ridge regression, if I say about the penalty, here penalty is much larger than this. Don't confuse the penalty of Lasso with the penalty of ridge. Penalties, they have their own, I'll say, style of calculating the penalties and own style. Like for Lasso, it treats all of them coefficients as equal. 1000 is equal to 1 and 0. For it is equal. It can for ridge regression, 1000 to 999 will give much higher penalty than 1 to 0 in ridge regression. So that's why ridge regression is choosing this. Don't confuse the penalty of that. We are reducing the coefficient from 1000 to 999, or we are reducing the coefficient from 1 to 0. Getting my point?
Yes, ma'am. Yes, ma'am. Got it.
Now coming to today's topic. Already half an hour is gone. Okay, let's start. So I'll just give you an overview of these things. I want that, okay, maybe I'll discuss, okay. Principal component regression. So before going to principal component regression, can someone tell me, anyone knows about PCA, principal component analysis? So these all techniques, as someone has asked me a very good question, why we are doing and all. Actually, it was not a silly one. It was actual question which should be asked, like why we are doing. We are doing just to reduce, like this is like a pre-processing step. What we are doing before actually starting the model and all.
Ma'am, what principal component analysis, what I understand is, say, lasso regression or this one, other regression type, it's just little different. Like we are projecting to another, like reducing the domain, but we are projecting to another hyperplane another line or something like that. That we are using, not the feature. Like whatever features we are doing, we are transforming the features value to another kind of values and which we are going to use it.
Yes. Absolutely correct.
Correct.
Now we are not using the same features as he said very well. We are actually transforming those features. We are actually projecting those features into principal axis or some X. I'll not say the now the terms, the terminologies. We are actually transforming. We are using that derived input directions. We are using that derived features. I'll say in easy words. We are using those features. We are not using the same features. That is the main difference. Now, how we are doing? What is first of all PCA? PCA is basically dimensionality reduction. There, what we were doing is we were just playing with like, okay, reducing the weights or coefficients of weights. Here also, what we are doing is we are basically reducing the features only. Like suppose I have 10 cross 5 matrix, n, which n is number of data points, f is basically, or 5 is basically the number of features, suppose n cross d, the number of data points, and 5 is the number of features. Here I'm reducing it, suppose 10 cross 2. So I am reducing the number of features from 5 to 2 basically. So this is dimensionality reduction, PCA. But here, when we are reducing it, we are not using the same inputs and feature like input features. Basically, we are basically projecting them. That's what he said. Now, how we are doing, how we are reducing the dimension? Can someone tell me? I'll just write this step by step so that you shouldn't get confused, like what's happening. So first of all, we do the centering of the data. Okay, one more thing. I think one of you mailed me also. I haven't uploaded the notes in the drive. After this lecture, for sure, I'll upload this also. These three, I forgot that. And I'll also upload one example of this PC also. Because of the short of the time, I can't like explain you the example here. Maybe I'll give you the example in the drive only. Centering of the data. Can you tell me what is centering? I'm taking the data, I'm centering it up, then computing the covariance matrix. I'm just writing the step. Here, what we are doing, dimensionality reduction by projecting. I'll tell you what are the things, what I'm mentioning. So can someone tell me what is this? What is matrix? Yes.
Are you talking about PCA or PCR right now?
PCA. I'll come to PCR afterwards. This PCR and PCR related only. Just after doing PCA, we are doing the regression. That's PCR. Yes, Chavi, you were speaking something.
No, I was just answering that you were asking.
Okay. Yes, centering. Yes, can someone tell me?
We convert the matrix into orthogonal, that is centering.
Orthogonal, as we have done before, also like by to orthogonalize the dimensions or to convert the matrix. So we are doing centering. So what is the formula of covariance matrix? What is covariance of two variables? Very slowly we'll go. What is the covariance? What do you mean by positive? Okay, I'll go very simple words. What is positive covariance? What is negative covariance?
Covariance, positive means they are related to each other, negative means they are inversely proportional. So if one goes up, the other one goes down.
So if covariance is 0, they are independent, I can say. They are not related with each other. So how to calculate this covariance matrix? So basically we have the formula as I'm doing this. Or I can say simply. You got this, what I have written? Or divide by n minus 1, it's fine. Yes, come on. So what we are doing is we are this x minus mu means centering. We are basically subtracting by mean. We have already done before also in our previous lectures also. We are centering it. We are doing it so that they should be orthogonal, as one of you have said me. Then we are calculating the covariance matrix. So by this is the covariance matrix. Now the third step is maybe I'll have a like something like 10 cross 10 matrix and I'll reduce to 10 cross 2. I'll share an example with you guys in the drive. Hmm. Now, the next step, anyone knows the next step? Okay, we are doing the centering. We are calculating the covariance matrix. After that, yes, then we are calculating the eigenvalues and eigenvectors of this covariance matrix. I'm just writing the steps, though I think maybe professor has told to that he'll explain you afterwards in some lecture. But as you have to understand this PCR, it requires this. What is eigenvalue and eigenvector? Anyone? Come on. Am I audible?
Now, eigenvectors are vectors around which only increase and decrease when you transform a matrix or multiply on the matrix. It does not change its axis.
Yes.
And if vector would be if you take all the points in an eigenvector and move it to the if you take it perpendicularly down to the axis, the space between them would be values.
So can I say that direction, as you told that direction, that is basically the values.
Eigenvector is
Direction
the
is direct.
eigenvector is the axis and values are the spin.
Values are the eigenvalues. So eigenvectors, when
The
I'm
direction is correct.
hmm?
Yes, it denotes some direction, I think.
Yes, direction of maximum variance actually, where the maximum variance is, and eigenvalues is the direction. I'll say amount of variance along that direction. So as he said, uh, that direction only stretch, or I'll say like if I'll take a rubber, it will only stretch or shrink. That is eigenvectors. In other words, like I'm going to very detail. Like here, it's like either it will stretch or it will shrink. The amount of stretch or shrink, that is the eigenvalues. The direct basically which are shrinking and stretching only, that is basically the eigenvectors, and the amount, the factor by which it is stretched or shrink, that is basically the eigenvalues. Fine. Now what we are doing, we are basically first doing the centering in PCA, then we are calculating the covariance matrix, then we are calculating what are the eigenvalues and eigenvectors of these. Wait a second, let me put on charging the lab. 1 minute. Then the next step, order the eigenvectors by descending eigenvalues. Okay, I told you like we are doing these steps. Can you tell me the intuition behind this? Like, okay, why I am doing this. Told you the 4 steps, like we are doing so. Can you tell me the intuition behind them? Like why, what it can help me? The main motive is to capture the maximum variance here. Like components, which components are more important. I want which features are more important. So I want those features. I want where the maximum variance is captured. Those features which are capturing the maximum variance. So for that, I am doing this. I calculated the covariance matrix. Then what does covariance matrix tell me? Yes, what is it telling me? How the features they are varying together, how they are varying, how and then its eigenvalues and eigenvectors are telling me how is the spread of the data, how is basically the variance and all. Now what will be my next step? I order this in order of the descending values. Now pick k eigenvectors, top k eigenvectors. What is it? Is it going above your head, or you are getting the point, like what I'm trying to do?
Yes, ma'am.
So
Just one question. Are you right now just checking whether one feature depends on the other?
no, nothing like
Because that would be variance, right? Just
that.
checking the ones that are maximum.
Maximum variance. I'm saying that where the maximum variance, which features are actually capturing the most of the variance. That I'm saying.
Okay,
So
features variation along to the regression line, you mean? Like
what I mean is,
which feature explains the regression line
yes,
better?
yes.
Okay.
Don't go. Don't. Okay, leave. Don't think about regression line right now. I'm not talking about regression at all. Just which features are capturing more variance, which features are more important for my current data, like in my current data, which are the most important, which are the most prominent features, which features are capturing the most variance. That's what I'm saying. Then now suppose I have n cross d and I told you that I want to do n cross k. This k, like this, suppose this k is supposed to, so I'll basically pick up these top two eigenvectors and then I'll do the projection. So like, so this is the eigenvector projecting to x, basically projecting to x. So this is the eigenvector. This is how we do the projection on x corresponding to first eigenvalue. Then I'll run the regression. Now this is just the PCA thing. Now I'll run the regression on this PC scores, whatever there is. How we'll run the regression, I'll not tell. I hope so that you know that this X transpose X inverse, X transpose Y, this is basically the beta, and then we'll multiply with the beta. But now, one more thing. Now we'll do, rather than X, we'll do this Z. Now we have this projection matrix. I'll again come. Don't worry if you're not getting, I'll again come. Now I'll do this Z transpose, Z inverse, Z transpose Y, the same way we do the regression. That is what I'm trying to do. Then I'll do the regression step. The same way, again, this is the regression thing only. The main part is this PCA thing. First, calculating the covariance matrix. What it is trying to do, it is capturing the features which are more important. That is what the main motive of linear that lesser regression and all was also, that I want the more prominent feature. Its main motive is also I have to capture the more features. How I am capturing the features which are more important, which are having the most variance. How I'm capturing, I'm saying which are having the most variance, because the top k eigenvalues, the eigenvectors which are corresponding to my top eigen values, they are having the most variance actually. The covariance metrics that are basically capturing the most variance, that's what I am taking into account, and then I'm independently doing the regression, and then that is the main motive. This is the main intuition behind it. Maybe I'll give you an example through which you can see like how the step by step I'm solving it. Though I have told you in detail, this is the whole regression part only which we have done already. So this is the PCA part. Yes.
Ma'am, for each eigen value, we are doing regression
Yes.
independently.
Yes.
Okay.
Yes.
Would you just show the calculation for the regression line
Maybe
on PC once? Z transpose into Z inverse then?
ZY. Like I think we have done, maybe you will see the last lecture, na? We have done this X transpose, X inverse, X transpose Y. We have calculated the beta. Then we have done this X beta. The same way we'll do this. The same process of the regression we'll apply here. Just we are using this Z because we have calculated this projection matrix. So instead of X, we are doing this Z thing. Maybe I'll surely upload, I always forget, I'll surely upload the one of the examples, so that this, because we don't have that much of time, if I'll do the example, this whole class will go in PCR only, and we have many topics to cover. So that's why I thought, okay, let's give the intuition, let's solve the example. I'll give you the example in the drive, and you can check that example again. If you'll have doubt, mail me or ask class. These are the steps how we'll do. Any doubt?
No.
What about others? Yes, Gavin, Abdullah, Chavi, yes.
No, ma'am.
You got the point?
Yes, ma'am.
One doubt, I have one more doubt. Like how many eigenvalues we will take? Like there will be multiple eigenvalues for a given matrix. So how many eigenvalues will we define that these will be top features, others will be not?
Very good question. Can someone answer her?
The highest value of the PCI. So eigenvalue.
How many
I-
eigenvalues? That would be the number of maximum will be the number of dimensions, right? It won't be more than that anyways.
But
No,
how?
it's for the n by n matrix, we'll have the n PC, right?
You'll have an eigenvalues. Eigenvalues are capped to a number of minimum number of dimensions. So if it is 2 by 3 matrix, there'll only be 2 eigenvalues max. Because there'll be maximum 2 independent columns.
So these are the eigenvalues, as you said, that maximum will be D only. Yes, absolutely. Maximum will be D only. So if you are given with like, I want, suppose if I'm talking about PCA, I want 10 cross 10 to 10 cross T2 matrix. I want to do the dimensionality reduction. I'm talking about PCA, not PCR now. I want to do the dimensionality reduction from 10 cross 2 to 10 cross 10 to 10 cross 2. So what will be the K value here? How many eigenvalues will capture, anyone?
2.
2. So this is 2. So this is up to us how much we have to do it. If I talk about regression, then it's like we'll regress it and then we'll see the residual part and all. That is something different. This is PCM, how we do it.
Little off-topic question. Eigenvalues will also mean the number of independent features, right?
Eigenvalues, independent features, yes. It's a capturing the base. So what is the drawback of this PCR, anyone? Yes, come on. I know I have rushed through it. I haven't gone through examples. Still, I'll ask you, is it fine? What is the drawback? Okay, what is PLS? Yes, what is PLS? What is drawback of PCR? Oh, yes. So basically, are we considering the outputs also here?
No.
So what we are doing in PCR is we are only finding the direction X which has highest variance. But here we are not saying which are inclined to output Y. We are not at all talking about the output Y. We are only saying which has the highest variance that we are capturing. That's it. But if I talk about PLS is basically what they are doing is which they are considering the output into consideration. Like they are using the Y as well, the output as well. They are not only looking in the input, they are also looking at the output. They're considering that output direction also, how the output is also changing. So there can be sometimes the flaw when we are only looking at the inputs there and the output. When we are looking at the output also, then comes the PLS, partial least square method. So what they're doing is they are also considering the Y here. Again, I'll give you the recap or only like not recap, only the gist of this PLS. I'll now for this PLS, I'll give you some a numerical which you have to solve so that you should also do some effort here so that you I want to know that these things, are you getting it or not? You can mail me after solving so that I can know that you guys are getting the things or not. So can someone tell me? First of all, tell me, like, have you solved the assignments now? You have solved the assignments, the assignment 2 and all. This is assignment 2, week 2. That's why I'm rushing because it's week 2. Now we are at week 4. Today's week 4th lecture. So that's why I'm rushing. Partial least square, like, any idea how partial least square is happening? What are the steps involved in partial least square? Yes, come on. Okay, I'll tell you simple in English. What is partial least square? First of all, find which features matter the most. That is what we were trying to do in PC also. We were trying to find which features matter the most. How we'll find? We'll do the correlation here. What we'll do? What we'll do? We'll say how strongly each feature here is related to Y. Or in other words, which feature is important for predicting Y. Take it so that it shouldn't be confusing. Suppose I have this sample 1, 2, 3, 4. I have the x1, x2, x3, x4, and xy here. I'll take what not to take. Okay, let's do. Simple intuition I'll give 1. Let's not take x4 for a while. So what I'll do, what I have said, can someone tell me how I'll do what I have said first of all? It's looking to me like no one is getting anything. Yes, I want very much interactive session. You should all participate, not only 2, 3. Yes, come on. Now what is the first step? What I have written? So I'll compute the correlation of each xj with y to know that which feature is strongly related to y. So how I'll do? I'll calculate, suppose this is 511. I'll calculate this. Xj y. This is 51j, 511. If I say 511, what is the value of 511? 1 into 2 plus minus 1 into 1 minus 1, sorry, plus 0.5 into 1 plus minus 0.5 into 2. So I'll get this scores. Not scores, basically the correlation between them. 4.5. Similarly, I'll do for 512, 513. Suppose I got this. Though I was thinking to give you as a homework problem. So this is the correlation for each of them. So first step is what I have done is xj phi 1j is equal to xj y. What is phi 1j? You got the intuition what I have written? 1 into 2 plus minus 1 into minus 1 plus 0.5 into 1 plus minus 0.5 into minus 2. So how much this feature, this all samples, this feature is correlated with this y? How much this feature x2 is correlated with this y? How much this feature is correlated with this y? I find out this. Fine till this step. Should I proceed?
Yes, ma'am.
Now, the next step is I calculated the score. What is the score? I'll tell you. Take all your features and combine them into single new variable. Using weights. I'll tell you what I have written. Now, this I have done, like how much it is correlated, how much x is correlated, or I can say I can also think in one way, like okay, this feature is this much correlated with this y. This is the weight associated with each feature. So now I have to calculate the score. How I have to calculate the score? I'll tell you. Now, can someone tell me what I have written and what I'm doing? Yes, come on. Is this confusing? Partial least square, like you have seen the lecture. How was it? You got the idea or no? Now you are getting it, what I'm doing. Tell me, I don't want a class where only I am only.
You're multiplying the variance with the samples again.
We calculated the correlation values, and then we are creating a new equation using those correlation value and with the along with the features.
Yes, absolutely. So, yes, one more thing. Who was there? I forgot the name. Gaurav. This is not the variance. This is the how much one feature is correlated with the output one, which means it can be it can be taken as a weight as well. So what we are saying is now we are calculating a score. The score is like, now what I'm doing is, as you can see, I'm having this weight. We can consider this as weight. How much each feature is having, contributing to this. If I'll solve it, you can see how I'm solving it. Suppose the sample one, I take it 1, 2, 3, 4, Z1. What is the, I'll solve and then I'll explain. This is 4.1511. 4.1 or 5. 4.5. Then X1 is 1 plus 0 into X2, which is 0.5, and X3 is minus 1. Okay. 0.5 plus minus 0.5 into minus. This is the score now for each sample I'm saying. This is the score I have calculated. What I have done, I have taken all the features and I am saying, okay, this much of weight for this sample, this much of weight, I have calculated the weight, like how much correlated is this. I can think of it as weight. So this much of weight is contributed to this. So let's take this weight 1 into 0.5 plus 0.5 into the zero weight. I'll give the zero weight to this feature. I'll give this much of weight to this feature. And then I'm combining this. This is the score. Got the intuition? I'll repeat it again. Come on.
I got it.
Yes. So can I say this score basically here, it is capturing the best part of X that predicts the Y, because it's capturing the weight associated with that. So it's capturing the best part of X. Am I correct by saying that?
Yes, ma'am.
Now, what's the next step? Anyone?
We will calculate the score.
Now we'll predict the Y using this score. I have calculated the score. Now I predict the Y using the score. How to predict the Y? What do? We calculate the beta usually. How we calculate the beta? X transpose Y over X transpose into X, or I'll say XY into X. But now, what is this? This is regress. Basically, we are regressing. That is what we are doing. Use this force to regress Y. Now, what we are trying to do is some theta value similar as this. What is this regress step we have done earlier also? Calculated this beta, calculated this. What is this step? Can someone tell me? Step 3 is, okay, first step was calculated the covariance, calculated the weights, then combined all the weights and added those features by combining weight and got the score. Now we are doing this regression step, this regress step. Like, what is this regress first of all? We are like when we have something X, we regress to Y, which means I have this input. I have done in multivariate regression also, linear regression also. I have this input. I am predicting the Y from this X. Now the similar way, when we are regressing on Y, regress Y, use the score to regress Y, which means I have Z1. Now instead of X, like what we do in beta, I have this X. I do this beta thing. I X transpose X over the same thing. Now, instead of that, I'm doing this theta thing, and instead of x, I'm using this z1 because I have replaced that x with the z. Got it?
Yes, ma'am.
Yeah. Come on. What about others? Yes, Chavi, Dharma, Gaurav.
Just
Yes,
get 3 ones more predicting y using the score. We got Z score you've taken out for each and every sample, and then is the feature into the correlation.
Can someone explain what I have done till now?
And first we calculated the correlations value and we found the highest correlations for each value. And then we use those correlation value to calculate the new variables, that is Z1 with highest with that with the highest correlation. I'm sorry. And then using those scores, then we will regress those, take the score as X. Now that no score will work as our input value, and we will regress that input and predict the value.
Yes, absolutely, absolutely. Now, this I'll leave up to you. Now, this I'll tell you this numerical value I want you should solve through this PLS. This whole, I have given you the formula as well. Just solve through this PLS. Say the whole thing. I'm not going to solve this example. Once you'll solve through by your hand, then only you'll understand how this is actually happening. Now, what's the next step? We have run the regress it. Now, we have done the covariance and the correlation, find the score, then regress. By using that score, we have done the regress thing. Like rather than using the x, we have replaced it by the this z thing. Now, what is the next thing?
If you just one question, ma'am, these brackets over here, what do they mean? Just what do they mean? The brackets, just the brackets.
This one, na? This is
Yes.
inner product. When we open this bracket, that's
Inner
what
product.
that's what I'm writing. This A B means A transpose B. You got it? The Z1 Y means Z1 transpose Y, Z1 transpose Z.
Okay.
Maybe you forgot. I told you earlier also.
I'm sorry.
It's fine, fine. So now what's the next step? Come on.
Now we try to see that our predicted y, the gap between predicted y and the actual y.
Your voice is cutting. Can you repeat?
I'm saying that now we'll calculate the gap between our predicted output and our actual output.
Okay, gap. One thing you are missing, we have usually done before as well, like orthogonalize. Not only centering, orthogonalize, we have done in multivariate regression. Anyone remember?
Yes.
So what was that? Can I say we are removing the influence of the above before one? Like if I'll write this, I'll not write this, I'll write gamma. What is this? What I'm doing here? I took Z1. What was it? X1 as Z1 only. Whatever it was. The X2 value here is whatever there is in the first one. I have to remove that. Whatever is like colliding with the next value, whatever the collision is between the first wave feature and the second feature, I have to remove that. That is what the orthogonalize means, that they have to be independent of each other. They have to be removed from each other. This we have done.
Yes, ma'am.
Yes. So this gamma here is again because here we are dealing with this x and z. So here it's like z regressing into basically x. So this is output here and this is the input here. So that's why we are using this gamma here. So now we'll repeat these steps, again find out the score, again do all this, and then at the end we'll combine all the score as you said, and we'll predict the y by combining the scores. This is basically y is equal to x beta, that at the end we'll do this. So this is basically PLS. Again, I'll tell you, solve this example. If you're unable to solve, then uh, tell me in the mail, or we can discuss in discussion. Obviously, it's tough. Tell me in the mail. I want that you should at least try. How much you will try? Give me that. Okay, we are at this point, ma'am. We are unable to get to the next point. How to do, so that I can help you with that. If I'll only speak in all the lectures and you'll listen, you'll say, okay, okay, I'm getting it, rather than trying, things will not work out. Mayank, I can't do the lectures on Google Meet, as I have the Zoom subscription only, not Google Meet subscription. So it's tough for me. Uh, the Zoom is creating any problem? Like, why you're asking that? Anyone? Like,
No, ma'am.
Okay. So now we have done this PCR as well as PLS today. In PCR, we discussed how we are doing. We are capturing the variance, and then we are doing the regression thing. Like, that is what we were trying to do in PCR. We did this PCA thing. We are capturing we are saying which of the features they're capturing the most variance. We'll consider those features. That was PCR. Now in PLS thing, we were basically correlating with Y, and we were saying which X is basically having the which X is more inclined to Y, which feature is more inclined to Y, basically. That we are taking into consideration. Then we are also doing the other things, like we are calculating the score, and that is whole step. The main idea was this: we are calculating the score, then we are regressing it, and then we are orthogonalizing it. Mayank, I'm not getting your point because my voice is coming to you, what I'm asking on Zoom, but on Meet it works. I'm not getting what you're trying to say. So can we move to the next step? Next topic. Are these topics clear? The gist of it, though I know I haven't given the example and detailed thing because of the lack of the time. Are these things clear? You are getting the intuition behind it, how the steps are actually happening in the class, or no? 31 students are present. Are those, I'll say 29 are present. Everyone is getting that?
Yes, ma'am.
Yes, ma'am.
What about others? Please give thumbs up if you are getting it. If you are having any doubt, ask me. There should be one thing only, either yes or either no. Ask me, like, tell me on my face I'm not getting. I'll repeat the things. I'll try to help you out. So now, going to linear classification. It's a simple topic. What do you think? What is linear classification? Yes, come on. Linear classification. What do you think? Yes, yes.
Maybe it linearly classifies the data.
Can I say separating the classes by linear? Yes, linearly classifying, linearly separating the classes boundary, having a class boundary, linear class boundary between the classes. That is simple linear classification. How can we do it? Yes. So One is through discriminant function, modeling discriminant. I'll not go to detail in the, I'll not go to the jargons and all like technical words. A simple function, I'll say. Simple function, what do you mean? What can these function do?
It will separate, I mean, it will form a line that will separate the uh, classes.
So it will form a line that will separate the classes. Or if I say, what do you mean by that? I is equal to 1 to k. These are classes. What do you mean by that? So I'll tell you how this is going to, as you said that, okay, it will give me a line which will separate the classes. Suppose like I have a function, it will give me an output. If the output it will give me, that is, if the function, like I have the function, I'll say for each class, if the output of one class is greater than the other class, I'll say, so which means that first classes basically, this data point, I'll have the data points, this data point belong to first class. If the output is having giving me delta 1 greater than delta 2, which means it's in the second class. Okay, a simple example which we were seeing earlier also, that was of KNN majority. Like we were seeing of the KNN also. What was that? Like there was a simple K nearest neighbor. I said that, okay, this plus points in the training we have done. Suppose this is some point. This is in the 4 times in the training it's coming in the class 1, and 2 times it's coming in the class 2. So majority function I'm using here. This function, there is some function, I'm using the majority function. So output, which is the more output, class 1. So what I'm saying is that it belongs to, this point belongs to this class 1 basically. That is what I'm saying, that whichever will give me the higher output, to that class it will do belong. Is it clear? Simple. Any doubt? This is lean. Maybe I'm getting like telling you in the complex words. Can someone explain very easily what I'm trying to do? Very simple concept it is. Yes.
Ma'am, in this, what we are trying to do is that we calculate this psi 1 and psi 2 and see if, we'll see which one is greater. And then whichever is greater, we'll choose that for
Yes.
the projection of that
Yes.
line.
Yes. Yes. So simple. So whichever output will be greater, we'll choose that class. That's what it is trying to say. So when we do this linear classification, I'll simply jump. I'll not go to detail about the probabilities. What is the drawback here? Maybe you have done that when we are doing this linear regression type of thing in the classification, linear classification, we do have some drawback. Suppose professor has also told about, I just jumped to this masking. Can someone tell me what is this masking? The professor has told what was the drawback. I'm jumping because it's an easy topic only, so that we can go to the main things. What is masking? Okay. First of all, I have two classes, 0, 1 class. Okay. Now tell me what is masking.
A point might be of zero class, although it is after after the line it ends up in class one.
Yes, yes. What
If
has
it,
happened?
and for example, we say if it is high in x-axis and y-axis is class, it would become class one, but actually it is not the case.
Ma'am, in simpler terms, we can say that masking is that one of the x is not being considered. It is so small that it is not being considered. It is being masked by the others. It is never getting chosen.
So basically, masking here means like there is a drawback when I try to do this linear classification. When I try to do the simple linear, trying to fit the line here, simple by linear regression or something. Like suppose I am doing here these points here, say me that it lies here, class one. For other points, it's zero, and for here, it's like one. And these points say me. Suppose these are the other points. Sorry. These points are here, lying here, and for other things, they are zero basically. This is basically class one, suppose, and this is basically class two. If I have to fit a line, how I'll do, I'll basically draw here. If I'll try to fit a line, I'll draw this. Now I have class three, which is here, which I'll draw somewhere in the mid, or I'll say I'll fit a line here for class three. Now for class one, if I say class one, the points are greater in majority. They are one. When they are one, the output is one. Basically, when the output is one here at this point. In class two, the output is one, two till this point. Now, what is the issue here? Can someone tell me the diagram only? These data points belong to class one. These data points belong to class two. Can someone tell me what is the issue here?
They are not correctly mapped to class 3.
Yes. How? Is there any place where class 3 is dominating?
No.
Those points can be considered both as class 1 or class, well, sorry, class 2.
So some points can be, whenever the some points will say come, I'll say whichever delta is higher, I'll choose that delta. So either class 1 delta will be higher, either class 2 delta will be higher. Never class 3 delta will be higher. So either this function, either the points will belong to class 1 or either the point will belongs to class 2. Never the output will point to that the input, like never it will be like that the class, the points are belonging to class 3. This part is basically the concept called masking. What I'm trying to say, where no, here the class 3, there is no output space where it is dominating. These are the inputs, these are the output. Here it is never dominating. Either class 1 is dominating in some inputs, either the class 2 is dominating in some inputs. The class 3 is never dominating. That's why we came up maybe that's why we came up with the idea logistic regression. How logistic regression can solve? Yes, come on. So instead of regressing on x, what we are doing, regressing on x square in logistic regression. X square, which means the line will be like this, the line will be like this. And suppose maybe the center line, class 3, we can have this. So I can say till this point, class 1 is dominating. This point, class 2 is dominating. And this middle point, class 3 is dominating. So here, each and every class is actually dominating here. Do you got the intuition behind this? Yes, come on.
Yes.
Yes,
What
ma'am.
about others? Mia, why your doubts are not reaching me? Like, can you, I am able to hear everyone's voice. Ma'am, can you unmute yourself and speak? Like, what's the issue? Like, so that I can help you. Okay, your voice is not reaching me. Uh, can you again log out and log in? Because I don't think so for others. For me, changing into Google Meet, it's like impossible. Like, I have this Zoom subscription, taken this Zoom for me, and I can't say this NPTEL people like to change this. So for me, it's not at all possible. Can you again log out and log in? Or one thing is like you can maybe you can use some other device as well. Like you can log in through two devices, like phone or a phone, and one you can mute it, and you can ask the doubt from the other phone. You can log in from phone and ask the doubt, and you can see on the laptop if possible. Or you can write on the chat. The worst case is like you can write, obviously if you'll speak that will be more clearer to me, like the doubts and all. Worst cases you can write, you can mail me as well, like that's the other thing. But in the meeting I'm saying that use some other device as well, so that you can and see, because others they are able to reach me out.
So, ma'am, my question would be that in normal classification, because it's just a 2D plane and the values can go from infinity to infinity, we can't get it. But in logistic, all values can be in like a 0 to 1, and then we can classify, we can break it into classes in 0 to 1. Is that what you're trying to say?
I'm trying to say, like, here it's forget about that 0 to 1. What I'm trying to say here is, what is the intuition behind it? Why I'm trying to go to logistic regression is, there are some classes which never dominates. Like, suppose the class 3, they never dominates. Like, whenever the new data points will come, it will either belong to class 1 when I'm trying to fit a line, when I'm doing the linear regression type of thing, when I'm trying to fit a simple line, y is equal to mx or beta x, and then there is some class which never dominates. Never dominates, I'm trying to say it again and again. What does it mean? Like, it means like whenever new data point is coming, it will never belong to that class. Because what we say, that whichever function, but whenever the output of the function is max, that will basically, this is the output. Suppose this output is max here, this output is max here, and this output will never be max. That's what I'm trying to say. So this class, I'll never get the output as class 3. This happens when I'm doing this, trying to fit a line. So rather than trying to fit a line, I'm saying let's go to x square kind of thing, that is logistic regression, so that every class should actually dominate, so that the results can be like every class output should have some result of the every other class. Yes, Chavi?
So, ma'am, this you mean that if we are introducing new data points in class 3, so they will never be considered, or they will be considered as the data points of class 1 or class 2?
Class 1 or class 2.
Okay.
Hmm. Hmm, hmm.
I mean, even if we are introducing in class 3, it will be taken as they are the data points of class 1 or class 2.
It can happen that because the output will always be like, okay, it's confused because the dominate class 1 or class 2 is dominating. So even though they are the data points of class 3, but we are saying that, okay, but the function is actually output is giving me class 1 or class 2 dominating. That's why. So that's why here the problem is solved here. Uh, your doubt is solved, Gaurav?
Yes.
Chavi, okay. Gaurav?
So if it's a curved line, you have more ways of classifying it.
Yes, yes, yes. So now coming to logistic regression. Now again the mathy part will come actually. Don't get scared. Just write it side by side. Hmm. What is log odds? Okay. What is probability of odds? I'll try to do it as simple as I can. Probability of success over probability of failure. This is for what we called as probability of odds. Now, in logistic regression, what we do is we, rather than doing that, because it's not in linear and all, we do the log odds. We, rather than like we try to fit a linear model to log odds thing, which means taking the log of it. Log of, what does it mean? The same thing, probability of success and probability of failure. Just taking the log of it, that is what it means. And trying to fit a linear model. Trying to fit a linear model, which means any doubt till now? Then we come up with the sigmoid function. Okay, I'll just solve it, how we are coming. Any doubt till this step? Now I'll go very slow. No rushing up. Yes. Okay, clear. Mhm. Now I can see your thumbs up, man. Yes. Okay. Mhm. Can I do? Whenever we are log is here, we can take the exponential on the other side. Fine. This is simple maths. Don't worry. Just taking this to the right hand side. Just opening the brackets. Taking that to right hand side. Taking this to right hand side. Dividing by e raised to power beta naught plus beta 1x, 1 over e raised to a 1 divided by this is e raised to a minus beta naught plus beta 1x, and this is 1. This is p of x, which we call it as sigmoid function. Now you'll say me that, okay, we don't want derivation and all, but obviously you should know, like I'm not saying you should know. This is actually the steps, how we are going from this step to next step. Okay, who has, yes, Mia? Yes, yes. Unmute yourself, try to unmute, but should be minus. Is it fine?
Yes, ma'am.
Yes. Okay. What about others? You got how I have calculated this P of X?
Yes, ma'am.
What is P of X? I'm so sorry. Before jumping, P of X, what is P of X?
Probability of X occurring.
Probability of X. I can say that if I say about the binary classification, the class is equal to 1 if X is given to me. That is basically P of X. What is the probability that the class is equal to 1, the success when X is equal to X? So this is the sigmoid, this function, we call it a sigmoid function. This is how we derive it, the log of odds and all. I'm not going like to unnecessary derivations, I'm again saying. So this is how we derive it. Clear? Should I proceed?
Yes, ma'am.
So if I talk about logistic regression, it's basically a very powerful classifier, I'll say. It's also used in sensitivity analysis. This I'll say you, I'll just give you a task like how it's used in sensitivity analysis. Do check and tell me in the next lecture how it's contributing in the sensitivity analysis. This is your work, which you have to do. Now, okay, multinomial logistic regression. Anyone can tell me what is this? How we are getting this? Any idea? You got that? That was that formula of this is the same thing. This P of X is the same thing. You get this when we have two classes, binary classes. This is the sigmoid function. What is this? How we got this? Any idea?
And here we have multiple classes.
How we
So,
derive this?
ma'am, by taking summation, maybe.
I'll just give
By
you.
product, right?
I'll tell you. So whenever we do, as we have done that, we do log of odds again. I'll do the same thing we have done. So what I'm trying to do is log of there. What I was trying to do is log of P of X over 1 minus P of X. Here it's like whatever the class, success class, K class, and any reference class. It's some reference class I'm taking log of PK of X and success over failure. Rather than that, I'm taking some reference class PK minus PK over X. Now we know that it's equal to beta naught K plus beta. I'll not maybe K and I don't, maybe there can be some confusion here. This is equal to this. When, okay, sorry. Then more about this.
What is the numerator here?
PK of X.
PK of X by PK of X.
This is small k, this is the large k. Capital K. So this is a baseline K. Whenever we do the multinomial, we have multiple classes. Some base class we usually take PK, that is the K class. Rather than taking all the classes, I'm taking some base class here. Now, I'm taking this class there, PK of X. Okay. Okay, again, there it will be this maths part will be hectic for you. I'll write 1 minute. Let me write, then I'll explain. I'll write it up, whole thing, then I'll explain. Can someone try to decode it, what I have written? Yes, at least try. Come on. So it's just the derivation, how I come to multinomial logistic regression. This formula, like earlier we have the sigmoid formula by log odds thing. Again, I'll say you take it as homework problem, like how I'm trying to decode it. I'm giving you the solution also, how I'm trying to decode it. Just try to see these things, like what I'm doing. I'll give you an intuition. This is the base class. Rather than taking the failure thing, we usually take this base class, and just I have done this. The summation is equal to 1. And this, if I talk about, this is e raised to power 0, so that's why it's equal to 1. And then adding up all the classes, rather than this k is equal to 1 to k. So this was the k class, and this was the other k minus 1 class. Then I have taken the uh, common here, and then uh, this is equal to 1 basically. And then it has gone to the right hand side. Then I have set. I'll not explain, or I'll not go in detail. I'll tell you to look at this if you want, because otherwise, obviously you should see this multinomial logistic regression, how the things are going in this log odds, how I have done this. The simple thing, I have given you the intuition behind it. I'll not go in detail with this. Now this is multinomial logistic regression formula, and this is what we have done this, the simple sigmoid formula, the upper one. Can someone tell me about Bernoulli distribution? Have you heard about this? This is exponential. Okay. Someone is asking, Mayank is asking, how in the first one, in this one, you have converted this E is coming. So basically, this is, if you'll see here, PQ of X into E. That's what I have written. This PQ of X is this capital X I have calculated, and then I have multiplied by this term, E term. Got it, Mayank? Am I rushing? Are the things clear? This PQ of X multiplied by this. PQ of X I have calculated here, and then I have multiplied by that E of X exponent. This is how it came. Can someone tell me about Bernoulli distribution?
Bernoulli distribution is same. It's binary. It's what either.
So it's like either when we toss a coin, either it's heads or either it's tail. Basically, that's basically the whole. So basically, what we are saying, either the success or either the failure. This is a kind of Bernoulli distribution. And if I talk about here, here also we are using the Bernoulli distribution. As you have might seen that when we are calculating this likelihood, the professor might have seen. So this is the formula of the Bernoulli distribution. What is there? P of X. So probability, like if I say, what is the probability that, I'll take the simple example how this formula came. Y is equal to 1, the output is either 1 or either 0 in head or toss, in head or tail case in the coin toss. What is the probability that Y is equal to 1? So what we do, probability over success, 1 minus probability into failure. Or if I say that probability is 0.7, probability of head is 0.7, then the probability of tail is 0.3. So it's like either this will come or either this will come. Either the head will come or either the success. So probability over the G1 output, either this class will be there, failure into 1 minus G1. Either this class will be there. So this is basically the Bernoulli distribution they have used. Are you getting confused?
No, ma'am.
Till what point, like you guys have understood? I'll go again. Sorry for rushing. Maybe
Only the multinomial after the point where you said it's equal to 1, I get it. Sum of all probability is equal to 1, but then what did you do? That's it.
What about others? Chavi? Meghna? Medha?
Can you please tell about the Bernoulli distribution principle?
Okay, before that, Chavi, have you understood what I have done?
From the derivation part, I'll try to do it again by myself and then I'll ask you in the next class.
Okay, okay. Okay. So Bernoulli distribution is nothing. Okay, I'll come to you also. This derivation also. I'll maybe actually I have to go somewhere. So
Okay, ma'am.
maybe
We can take it. I'll email it to you.
no, no. It's Gaurav. I'll basically explain you. Maybe we'll take this multinomial logistic regression in the next class. I'll go again with this derivation, whatever you have tried, whatever confusion is there.
Sure.
I'll try to make you understand about these things. I'll try to cover this whole part as well as the next week lecture in the next class.
Sure.
So any doubts till now? Maybe I have to rush, so that's why. Yes, any doubts? Let's stop the recording.